Now let's do an exponential decay problem. This is going to be very similar as the last one. A town currently has 52,000 people. We want to write a function to model the town's population if that town is decreasing by 10.3% each year. So this is decay, which means that in the parentheses is going to be 1 minus the rate. And your rate is 10.3%. That's going to be 0.103. So this is going to be your starting value. This is going to be your P. And let's plug those in. A equals P, parentheses 1 minus the rate to the T power. 52,000. 1 minus 0.103 to the T power. And then we want to combine the 1 and the 1.103. So I'm going to just do 1 minus 0.103. And I get 0.897. So I'm going to write my final function as A equals 52,000, parentheses, 0.897, raised to the T power. And that's going to be your decay model. And it's decay because that number in the parentheses is between 0 and 1, so it's going to be decreasing. So now let's apply how to solve for problems using that function. So here's your function, 52,000.897 to the T power. We want to know how many people will be living in the town in 8 years. So this is like just plugging it in. We want to know what is going to be the A value after our time is 8 years. So we can put that right into the calculator and figure that out. So 52,000 parentheses 0.897 shift 6 raised to the 8th power. So after 8 years, it looks like 21,794.298. These are people, so we don't have to be decimals here. We can round to the nearest whole number. So I'll show the work. It's not much. You just got to write this with the 8 in there when you're writing your work down. And then put your answer. So your amount is approximately equal to 21,794 people. After 8 years. So that's a quickly decreasing population. Now let's analyze, trying to figure out a time. So we want to know how long is it going to take to reach 10,000 people. So like we did in the previous example, you could guess and check. So you might say, let's try 20. All right, 20 years is too large, so maybe 12. That's a little bit, not quite where we need to be, 14, 15, 16. So it might be somewhere between 15 and 16, because at 15 we're above 10,000, but at 16 we dip below. So maybe 15.5 or 0.4, 0.3, 0.2, 0.1, somewhere between 15.1 and 15.2. So you can be more precise as you go out, but I encourage you to use the intersection model. So with the intersection, we'll put that function in with x as your exponent, and you'll do y equals 10,000. And we're going to zoom out one more time. This is a very, very high value here. So 10,000 is way up here. So you're going to drag your cursor all the way up, and you're going to see where 10,000 meets this graph. And it's about 15.167. So I would probably bump that up to 15.2 or 15.17 years. So A is approximately, or T is approximately equal when this is 10,000. T is approximately equal to 15 point, I'll say 2 years. Doesn't have to be exact, but I like to go at least one decimal place out when I'm rounding to years. All right, that's how you do an exponential decay problem.